This video is the second part in our discussion of transport category aircraft electrical systems. In it, I will be covering AC electrical control and indication. What you see on the screen is an electrical schematic on the left for a pretty typical twin-engine aircraft. This is a split bus design. And then on the right is the associated electrical power control panel that would be located in the flight deck. And we're going to focus in this section on the AC portion. And so on this, on the schematic here, the AC portion is everything in this upper area. And the control for that, also the controls that align with that, are also in the upper half of the control panel. So the first thing here we'll see is this has, as I mentioned a second ago, this is a twin engine aircraft, so there are two main generators. There's IDG1 and IDG2. And then the controls for those here on this AC electrical panel, there's an IDG1 control and an IDG2 control. And the way those work is most of the time these are left in the auto position as shown right now. In the auto position, this knob controls the generator control unit, or GCU. That's this thing shown here, and there's one for each generator as well. The generator control unit is a computer or logic controller that turns the generator on or off, whether it's going to put out any power or not put out power. It does that by turning on and off field coils within the generator, and we'll discuss that in detail when we look at generators. But in the auto position on this, which is a fairly modern aircraft, this is the Embraer 175, so very modern. The auto position means that if the engines are off, the generator is not going to run. But once the engines are running, once they get up to a normal speed, the generator's up to normal speed, the generator control unit will sense that, and it'll automatically bring the generator online, in which case then generator 1 normally would power AC bus 1, shown right below it. And so that's where this arrow, so this left knob is going to control the left generator. Now we do have the ability, if need be, to manually move it to the off position. That could be done by the flight crew in an emergency or an abnormal situation. Or we oftentimes would do that for maintenance purposes, for testing and other things like that. And then you'll also see there's a third position here. That is DISC, or it stands for disconnect. We'll look at that too when we look at the generator in more detail, but we do have the ability to actually physically disconnect the generator in case of a generator failure so that we don't cause an issue with the engine. So here we have the IDG1 knob controls the left number 1 IDG, which powers the left number 1 AC bus. We have a right knob, which is going to control the right side. I'll get rid of some of these markings here. And the logic and the way that works is exactly the same with an auto position, which it's left in almost all the time. We don't even, on an aircraft like this, it's not even turned to the off position. Even when we shut the aircraft down, it automatically shuts off when the engine is shut down. And then there is an off position if need be, and a disconnect position as well. But otherwise, normal operation will be in flight with both engines running, as the IDG1 left will power the AC bus 1 on the left side, and IDG2 will power the AC bus 2 on the right side, and they each have their own generator control unit that's doing that. Now these buses and the buses can be connected together in the event of a generator failure, but most of the time when both generators are operating, they're going to be separate from each other or split, hence the split bus. On this panel, you also have the ability to control the APU generator with this button shown here. And this button essentially turns it on or off. And so the APU generator is shown here, and you can see that APU generator also has its own generator control unit. And so this button, this APU gen button, is basically telling that generator control to turn that generator on or off. And again, the APU would have to be running for it to be on. And then that generator can supply power to both buses if need be. So, on the ground before engines are running, if there isn't an external power source available, the generator would typically be used to power the entire aircraft, powering both buses. In the center here, we have a knob that's for controlling the AC bus ties, and the bus ties are what can connect the AC bus 1 and AC bus 2 together. They're also what allow the APU generator connect. So in order for the APU, the APU generator power, it goes through this APU contactor, which is also controlled by that APU gen button. And then power would flow left and right to each of the buses through these bus ties. Again, this being a very modern aircraft, this is normally controlled in an auto mode. We got ahead of ourselves. This is normally controlled in an auto mode, but if there is a problem, the crew or for maintenance, we do have the ability to trip these buses open, and so that would cause the bus or these contactors, these ties, to open. So those are essentially they work kind of like a relay. They're AC bus ties. They're big contactors. Contactors are for higher current items. Relays tend to be for lower current items. But it's basically a big electrically controlled switch where we can trip it open if we need to separate the buses from each other in case of a problem on one side or the other of the electrical system of the aircraft. Here we have a button labeled GPU. GPU is ground power unit, also known as external power. And this button these square buttons are something called a switch light. So you can see this button, which is a push in, push out type button. The top half says avail, which stands for available. The bottom half says in use. So when a power cart is plugged into the aircraft, a ground power unit is plugged into the aircraft, and it is powered on and supplying power, then that available portion will light up. And then if you push in on that button, and it will switch to in use, and then power will go through the external power contactor that's right below the tip of the arrow, and it will be able to then flow again through those two AC bus ties out to the main AC buses and to the rest of the aircraft from there. So this is our ground power. So we have the ability to, shown here, we've looked at kind of primary power sources in the form of the left and right integrated drive generators or engine-driven generators, and then secondary sources in the form of the APU generator and the ground power, a ground power connection where we would hook up a ground power unit. In an older aircraft, and this is not only older, but this is one that has this is the parallel bus system, things were a lot more manual. And so what we have here, the 727 where we looked at the bus system before, but an older split bus aircraft would also have a lot of these same kind of things, where before, for a given generator or something like that, we would have kind of one knob that's in auto. If you look on here, this one has 3 different switches for each bus, having to do with things like generator field. So there's a switch for the generator field. And then right above that is for the generator contactor, which we can trip or close. And then on the top is the bus tie, which has to be manually operated every time. And so the bus tie switch for each bus is right here. And none of this was performed automatically. This was all, in this case, done manually by the flight engineer. An aircraft that's a little bit newer that didn't have a flight engineer, the pilots would still oftentimes have to do this kind of thing manually, be located on an overhead panel. So here we can see the panel, the control panel, actually has a schematic of our electrical system on it. So these three vertical panels here, that where I've circled it, they have a white line that extends across the top. That's to show the sync bus. Remember, we could use that sync bus to connect the 3 main buses together, or we could use it to distribute power to the main buses from the APU generator or the external power receptacle shown on the right side. Ground power coming here, or APU being able to come in from this direction. And so here are those bus ties. So this bus tie breaker is for powering this bus. What it's really going, I should kind of move my arrow, but this bus tie right here is going to be controlling this right here, rather than the bus itself. It's to turn that bus on. It's to route power from the sync bus to this AC bus 3 in this example. But it does that by opening and closing that bus tie breaker. Here's the generator control breaker or generator bus tie. And what's not shown here is there is going to be a generator controller, a little generator control unit for each generator as well. And the generator control unit is what this field switch is going to operate. And so that's going to be sending the signal to the generator control unit, which is going to cause it to energize the field coils in order to turn on the generator and have it generate power. If we look at the indication side of these, here's an example of an ICAS system, and now this is going back to that Embraer 175 that we were looking at originally, and this is the ICAS display for the electrical system. And so ICAS next in a later module we'll be talking about indication systems. So ICAS is engine indicating and crew alerting system, and here it's a set of display screens where in this case we can pull up what are called system synoptic displays, and we're on the electrical system synoptic display. It's shown in the upper right hand corner. And what this allows us to do is see the electrical system and also understand where power is flowing, where it's coming from, and where it's going to, what's being powered by what. And so if we put this next to a schematic, and now this is, even though it's a little bit different schematic, it's a schematic that a little bit more matches with the ICAS display, but again, still for something like the Embraer 175 aircraft. Whoops. And so you can see the generators here from the engines are at the top, and those can power the AC bus 1 or AC bus 2. We can see what we have going on right now, which is where an AC ground power unit is hooked up, and the schematics, this ICAS schematic, the green lines, you can see some lines are in green and others are in white. The white shows where power can be routed, but it's not necessarily traveling that direction currently. The green shows where power is currently traveling. So essentially what we have as our source is our AC GPU, and the display even shows us what that frequency, what the voltage, the frequency, and the load on that GPU are from the aircraft. And then electrical power from the GPU is being sent to AC bus 1 and AC bus 2 along the green lines. And then from AC bus 2, you can see there's a green line dropping down to, in the center, this is the AC essential bus, so that's being powered off bus 2 right now, but it does have the ability to be powered off bus 1 if necessary. And then those are going to power the AC essential bus, powers the AC standby bus, and then those also are powering our TRUs, which the TRUs, the transformer rectifier units, are what are going to generate DC. So the bottom half of this display, everything below this line, right? Oh, this line here, I guess the line should go about there. Everything below that line is DC. Let me redraw it so it's a little bit more what we should be looking at. So we've got AC above and DC below. And so we can see where AC power is being distributed. You can see for our engines, these engines are shut down right now, so the generators aren't putting out anything. But when they are running, we are able to see the voltage, the frequency, as well as the kVA, which is the load on the generator. That's kilovolt amps. And we use kVA for AC systems because we have to take into account something called apparent and reactive power when dealing with AC, and it has to deal with inductive loads being put on the system and everything like that. So KVA is the standard thing. Rather than just looking at amps, or rather than looking at power in the form of watts, KVA is 1,000 volts times AC, 1,000 AC volts times the amps being drawn. So take volts times amps divided by 1,000 gives you the value in KVA. Also taking into account things like reactive and apparent power, which is a vector calculation based on the fact that inductive loads are going to drag phasing, AC phasing out of sync and that kind of thing. It's more than we need to know for this, but just know that's why we have a different, probably a unit of load or a unit of current that it's actually a unit of power that you probably haven't seen before when dealing with DC systems, direct current systems. You can see down lower where we have direct current, the TRUs, which they're going to generate DC from AC. You can see the load on those is given just in amps rather than KVA, because then dealing with DC, you don't have to worry about the reactive and apparent power. So the big thing here, though, is just understanding that with this ICAST display with indication, we can actually see a live working indication or live working schematic of what's going on with the aircraft. Now, it doesn't necessarily show every component, right? We don't see these bus tie breakers shown, but they are indicated in a manner such that we can see things like, if essentially that's the green versus white. So if the line is white or green, so right now, if you look at the essential bus, AC power is coming down and powering the essential bus, but we could move this switch here if we wanted to get power off of bus 1 rather than bus 2. So that's kind of those switch, contactor, relay positions are for the most part indicated by the colors of the different what are called flow lines. So those green flow lines, the white where the flow lines can be connected but currently are not. Once power gets to the various buses, then we have ways of controlling it. And so these control and then also indication. And so this is how we branch off. We use circuit breakers on the various buses to branch power off to go to the individual loads. And we've got a couple different views here of what's going on. So there have been a couple different ways that aircraft have been constructed and that electrical systems have come together. Primarily changes that have been enabled by technology, and the changes that have made things either safer or simpler. And so there's a couple things going on. So first off has to do with arrangement. So now circuit breakers are arranged in panels where they connect from a bus and then distribute power out to various loads. And so on older aircraft, going up into those built, kind of designed and built up to the early 1990s, all the buses ran up to the cockpit, up to the flight deck. And the circuit breakers were on those buses, and they were right in the flight deck. And for many of them, it was on panels on the walls just behind the flight crew members, the pilot, the co-pilot seats, or they were on some side panels down by the someone sitting in a flight crew seat down by their knees. And so you had some high current stuff going on up in the flight deck. That was the main buses were traveling all the way up and were right behind those walls that made up the flight deck. After the 1990s, aircraft design built kind of the 1990s, there were ways to move the buses outside of those passenger and crew areas. And that is the bus work, the big, heavy, high current elements of the electrical system were located down in, typically down below the floor of the aircraft in what are called either electrical and equipment bays or avionics bays. But in order to be able to control different things connecting or disconnecting, essentially being able to control those loads being turned on and off or power being sent out. This necessitated the need for what were called remote controlled circuit breakers, RCCB. Now, it didn't eliminate circuit breakers up in the flight deck. We still had circuit breakers in the flight deck, but the circuit breakers up in the flight deck now were all low current, and they would actually be used to control the high current breakers located down below. So here's this old system on the left where both these low current control breakers, shown by this one here, so this breaker would provide power, and it was a half amp to a relay, and then that relay would get power. Here was the bus. Power from the bus would flow through a different big circuit breaker, high current circuit breaker in the flight deck. And that power would go through the relay out to the load. And, the load examples of these could be things like, hydraulic pumps or fuel pumps, big electric motors, and that kind of thing. And so it used to be you had these panels where you had hundreds or even close to 1,000 amps running on the buses right behind the walls of the flight deck. And now in modern aircraft, more modern aircraft, you still have these low current. So here's our half amp breaker up in the flight deck, and then the switch, which is usually used to control the device. But then you can see now the bus is no longer in the flight deck, and the RCCB here would be down in that avionics or equipment bay. And so now we can control that remote control circuit breaker using a switch and or a breaker up in the flight deck to provide power out to a load. And now in your latest aircraft now, not only have we gone to this design, but the control circuit breakers in the flight deck now are being replaced, and they're being replaced with things like the ICAS, engine indicating crew alerting system, or ECAM, electronic condition and monitoring system, which are the electronic flight deck setups. Those now have electronic circuit breakers built into them, so it's almost like a touch screen where you can operate them. And so those the screens in the flight deck are able to, through a computer, send a signal to the RCCB, remote control circuit breaker, to open or close, and eliminating physical circuit breakers up in the flight deck. I'll show some examples. Now here I do have a link to a video. If you pull up the slides online, you'll see the link there, and you can look at circuit breaker operation. But I'm going to do a quick aside just to show. So there's two primary types of circuit breakers. The first is a thermal. So thermal circuit breakers. And this is just a quick kind of reminder. So in a thermal circuit breaker, we have a bimetallic spring or bimetallic strip that is used to connect the two pieces. So here's our bimetallic strip, got two pieces of metal, different pieces of metal. And there's a wire coming in, and it's contacting a wire going out. And what happens here is if the current gets too high, if our current gets too high, when we have a bimetallic material like this, it causes it to flex. And so what was our original bimetallic, instead of being flat, one side's going to expand more than the other, and it will cause that bimetallic strip to bend. And when it bends like this, we still have the wire coming in one side, but it will break contact from the output side, and so now the current drops. Now, if this was the case, it would just bend like that, and we would lose our contact. But as soon as it disconnected, it would start to cool down. We don't want it to go back into place. So there's always a little kind of a hook right here that's going to keep it from going back down. And that's the part of the circuit breaker when it comes up, it pops our circuit breaker, and our circuit breaker sticks out. And so to reset it, when we push our circuit breaker back in, so that comes up, here's our little circuit breaker plunger, right? And so when we push that, if we push it to the right, that'll allow this bimetallic strip to drop back down once it's cooled and reconnect the circuit if we need to. So that's a thermal circuit breaker. That's one type. The other type is an electromagnetic circuit breaker. And in this case, what we have is we have our power coming in, goes through a coil, to one end of a switch. And so we have a switch right here. And then there's an output side, the output side here, the contact here. And so under normal operation, power is able to come in, it flows through this coil, and then out through the other side, out to our load. Now, if that current gets too high, this coil is going to generate an electric field, and so attached to the switch right here is a core, like an iron core. And so if the current from the coil gets too high, it's going to cause that iron core to pull up. And when it pulls up, it will cause the switch to open. And so if I'm not sure why it keeps doing that. Let's go back here. So if it goes into a pop state, so here's our coil, right? And now our switch is open, and the reason it opened is because the current got too high. Here's the output side. And so our current had gotten too high, and that caused this iron core to get pushed up by electromagnetism, and it pulled the switch open. And again, this may have like a little tab on the end or something. Again, there's going to be a catch that when it comes up, it gets caught under, so it stays in that open position. And it'll stay there, once again, until we have a circuit breaker here where we can push on it to reset it. But if there's still too high a current, once we reset it, power will start running through the coil, the electromagnetic field will get high, and it'll pull it open if it's too much. So that's a electromagnetic circuit breaker. Okay. So these circuit breakers are arranged in panels in the flight deck on older aircraft, and the buses came up, and then the circuit breakers were on them. So here's an example of that. So in this aircraft example that we have here, the E&A bay and the main buses are right here, and there's breakers attached to it, and they're going to send out power through these various wires out to all the different loads, which are all the little circular dots on the ends. Newer aircraft have it more distributed, and this is kind of showing the 787 being more distributed, but here it shows the 2 engine generators on each engine, and then there's multiple kind of bus locations in this aircraft where power is sent to those, and then power using remote controlled circuit breakers, or RCCBs, is then sent to the loads that are near each of those kind of control points. And for the most part, they're not up in the flight deck. Now, it does show a forward E&E bay, and it does show quite a few loads up in the flight deck. Most of those loads in the flight deck, though, are going to be more of your low current loads. Things like some avionics or smaller, some light bulbs and stuff like that. The distributed loads that are throughout the rest of the aircraft, those are your high current loads. Those are the things like the hydraulic pumps. Those are the fuel pumps. Those are in the 787 case, it actually has electric motor-driven superchargers for pressurization and environmental control. Those are your heated leading edges in the 787. But again, high current loads in order to do that. So that's why. So here's what those circuit breaker panels look like, and you can see in this case they're arranged by what their use is. So there's ignition breakers here for the engine. So these are a lot of engine panels, engine oil, pressure, and quantity, APU, various breakers for the fuel system and the fire warning system, those are the ones that are easy to see, but you can see all these different breakers. And so these breakers are all showing in the set position right now. If we were to have an overcurrent situation, they would physically pop out. And in addition to popping out at the base of the circuit breaker, when it does pop out, so this area that's hidden currently inside, when that pops out, there's a white band there. And so the breaker physically pops out and a white band becomes visible to tell you that the circuit breaker has tripped. Here's an example what those remote control circuit breakers on something like an ICAS system look like. Again, this is that Ember 175. And so, as part as I can blow this up a bit. So the normal circuit breakers that are in green are the ones that are in the set position. And then something that where it's sticking out to the right and has turned white, that's a tripped position. And then you can actually press this data button next to it, and it tells you more information about that breaker. It tells you what it powers. It tells you where the remote control circuit breaker is located down in the avionics bay if you need to troubleshoot down there. It tells you it's open. It tells you what the rating is, what kind of voltage runs through it, all kinds of things like that. Sorry, but this is the 787. I think I said number 175. This is off the 787. You can also hit this control button, and the control button allows you to come over here, and this is where you can try to reclose it. If it was in the closed position, there would be a button here to open it, to pull the circuit breaker. You can lock it in the position it's in a pulled position. So that's kind of what's been done to this one above, where it has that blue band. It's called a collar, and it says it's been for a collar, it says do not close. Maybe maintenance is being done or something like that. So the white, I might have misspoke. White is a pulled circuit breaker. It's one where you have pulled it. Blue band is collared. Trip circuit breaker down here is in orange or amber and says tripped next to it. And so that's one where it tripped, and you would have to you could hit data, and sometimes it will say there might be some more information. Sometimes you can pull up or control if you need to try to reset it, something like that. But this is all done on this, in this case, a touchscreen ICAS display. These are the low current control breakers that then are going to control some kind of in many cases are going to control a high current contactor or circuit breaker down in the avionics and electrical bay. So that wraps up this section, and I appreciate you watching the video.